So in Chapter 7, we're going to look at heat and temperature. So temperature is a measurement of the heat content of a particular substance. So it's basically what we measure with a thermometer, whether we're measuring our own body temperature or we're measuring the temperature of a liquid. So the human sense of hot and cold cannot be determined just by temperature alone. Conduction and humidity are going to affect the human sense of hot and cold as well. So if you think about going outside and you're looking at the forecast and it says, okay, it's going to be 80 degrees. Not so bad, right? But an 80-degree day with humidity is going to feel a lot hotter to us than if there was no humidity. So even though the temperature might be the same as somewhere else, with a dry heat, the way we perceive it really depends upon several factors. So looking at temperature, we're going to do some temperature conversions. We're going to talk about Fahrenheit first. And Fahrenheit is the temperature that we usually use here in the US. It was developed by Daniel Fahrenheit, named after him obviously. What he did was he placed a mercury thermometer in an ice bath, and he realized that at 32 degrees Fahrenheit, that was the temperature at which water freezes. He then also measured the temperature of water boiling, and it was 212 degrees at which water boils. So these two values you're going to want to remember. 32 degrees Fahrenheit for water freezing and 212 degrees Fahrenheit for water boiling. Looking at degrees Celsius. So this is the common unit of measurement for temperature in most other parts of the world. And Anders Celsius actually developed this scale. So he proposed a scale of degrees Celsius to try to make it a little bit easier. What I mean by that is you'll notice that the freezing point for water in degrees Celsius is 0. So this is an easy number to remember, much more easy than 32 with Fahrenheit scale. For boiling water, 100 degrees. Okay, so the reason for the degree sign is because they're basically making these scales based off of a certain degree. So here are some temperature conversion calculations that we're going to be using to convert between Fahrenheit and Celsius. So these equations will also be present on your equation sheet. So if you are converting between Fahrenheit and Celsius, you'll want to make sure to use the equation where Celsius is equal to, because Celsius is what you're solving for. When you use this equation, in the numerator we have F minus 32. So you're going to take the Fahrenheit value given to you in the word problem and subtract 32 from it. But notice there are parentheses around F minus 32. Make sure you have that top portion in parentheses, because if you do not, it will divide by 1.8 before it does the subtraction due to orders of operations. Looking at the next equation going from Celsius to Fahrenheit. For this one, when you are looking for Fahrenheit, you want to use the equation where Fahrenheit is equal to. And in this case, it's really just the previous equation rearranged. And you're taking 1.8 times the degrees Celsius and then adding 32 to it. The parentheses aren't necessary as it will do the multiplication before it does the addition. One unit of measurement used for temperature that you might not have heard of is Kelvin, represented by the letter K. Notice there is no degree sign when we talk about Kelvin, because it's an absolute scale. It doesn't have a degree measurement to it. It's named after Lord Kelvin. And what Kelvin is, it's the SI unit for temperature. So when we talk about SI units, back in Chapter 1, it was the international system of units that was decided upon in the sharing of information between the science and mathematical fields. Kelvin being an absolute temperature scale, the degrees aren't used. So what that means is you can't go below 0 Kelvin. So 0 Kelvin is the absolute lowest possible achievable temperature. 0 Kelvin is also referred to as absolute zero because of this. It is the temperature at which all molecules and all atoms quit moving. So if we could actually reach 0 Kelvin, life on Earth would perish. Nothing would survive. It's that cold. To calculate Kelvin, you simply take the degrees Celsius and add 273 to it. Notice I don't have a way shown here to calculate Kelvin directly from Fahrenheit. So if you are given degrees Fahrenheit and you need to get to Kelvin, you're going to have to first calculate the degrees Celsius. Once you have the degrees Celsius, you can then insert that in the following equation to get to Kelvin. So here are some example problems that you'll see on the video also present in the folder, showing how to use the three equations we just discussed going between Fahrenheit, Celsius, and Kelvin. So now let's look at heat. Heat is the spontaneous transfer of energy due to a temperature difference. So we always have heat transferring from the hotter object to the colder object until an equilibrium is reached. So think of holding a hot cup of coffee in the morning. Well, the coffee is hotter or contains more heat than your hand does, so it feels warm against your hand. And what happens is if you hold that cup of coffee long enough, the temperature is going to equilibrate. What that means is heat is going to transfer to your hand until your hand and the cup are the same temperature. This transfer of energy is caused by the temperature difference. Since heat is a form of energy, its SI unit is joules, just like back in chapter 6 when we talked about work, kinetic energy, and potential energy. They were all measured in joules. Well, heat, since it's a form of energy, its SI unit is joules. However, there's always exceptions to everything, so we're going to measure it in calories. So you can see at the bottom of the slide here, it says heat is also measured in calories and kilocalories. So I do have a conversion factor to go between kilocalories and joules. However, we shouldn't need to use it for this chapter. I just want you to be aware that you can convert between joules and calories. So this heat transfer that we talked about depends upon 4 factors. And this will help you remember the equation or vice versa. So for heat transfer, we need first of all a change in temperature. So no transfer is going to occur unless one object holds more heat than the other. So we need a warm object and a cold object. What also depends upon is the mass of the system. So how much of those two objects you have. Do you have more of the warm or more of the cold? So the amount matters. The material that the substance is composed of also matters. So depending upon what type of material, you might need less or more heat to raise the temperature. So an example is you need less heat to raise the temperature of alcohol versus the temperature of water. So almost think of boiling points of substances. Some substances will boil at a lower temperature than others. So the material does matter for heat transfer. And last but not least, the phase. So whether you have a solid, liquid, or a gas. So think of an ice cube. It is made out of water, which is a solid. That ice cube can melt and form a liquid. It's still water, but it's now a different phase. It's liquid instead of a solid. And furthermore, if you took that liquid water and heated it up on the stove, you could actually heat it until it boiled, and you would now have a gas, water vapor. Okay, so the phases are also going to affect the heat transfer. So talking about phases, let's look at the 3 states of matter. So we have a solid, a liquid, and a gas. So when we're looking at a solid, thinking back to the example of the ice cube, the molecules are not moving. They are stacked, and they are in contact with one another. So a solid, frozen in place, no molecules are moving. For a liquid, the molecules are now moving, because if you think of liquids, they flow. You can pour a liquid from one container to another. So the molecules themselves are moving, otherwise the liquid wouldn't be able to flow. You wouldn't be able to pour it. However, the molecules are still in contact with one another, just like in a solid. They're always touching. The last state of matter is a gas. And for this one, the molecules are moving so fast and they're so chaotic that there is no contact. Okay, so the molecules are moving and there is no contact. So why? Well, a solid is very low temperatures, and when we have low temperatures, what happens? Our molecules tend to move slower, sometimes so slow that they get frozen in time, almost like a solid being stacked, being in contact. When you heat an ice cube, you get a liquid because by putting heat into that solid, you're getting those molecules to move faster. Okay, that's why if you apply enough heat, you can even boil a substance such as water and turn it into the gas phase. So heat is required to change phases from solids, liquids to gas. Heat going into the system can change the phase of the substance. So now that we've talked about both heat and temperature, let's compare them. So with heat, we said it's a form of energy, okay, meaning it measured in joules. For our purposes, when we do calculations, it'll be calories. It can be transferred from one substance to another, always being transferred from the hotter object to the colder object. And the heat also depends upon the object's temperature, the amount of the substance that's there, or the mass, and then the type of the substance. So are we talking about water, an alcohol, a metal? What does this matter consist of? For temperature, temperature is a measurement of the heat content of the substance. The higher the temperature means the higher the heat content. And temperature is actually proportional to the average kinetic energy of the atoms or molecules. So thinking back to chapter 6, when we talked about kinetic energy, kinetic meant moving energy. So by saying that the temperature is proportional to the average kinetic energy, it just means the higher the temp means, of course, the higher the heat content. And if you're applying more heat, you're going to be making those molecules move around faster. And if they're moving faster, they have more moving energy, and their kinetic energy is going to be higher as well. So temperature goes up, kinetic energy goes up, because that's what proportional means. If one goes up, so does the other. In the same respect, if one goes down, so does the other. So if we cool something down enough, the kinetic energy will go down, sometimes to the point of 0, where the molecules are no longer moving. So let's look at the heat equation. So we're going to be using this in some of our calculations. And the letter Q represented here, that represents heat. Okay, so when you see the letter Q, it means heat. So Q is equal to mc delta T. So looking at what all of these mean, first of all, I said Q is the heat measured, the heat transfer. And when we measure it in this course, we are going to be measuring it in calories. So a good way to remember this is if you think about just calorie intake in your body on a daily basis. Okay, you're taking in a certain amount of calories from food because you use those calories as energy in your daily life. And heat is a form of energy. So the more calories from food you take in, the more energy you have or calories you have to expend out. So how do you figure out the heat content in calories? Well, first of all, you need the mass. So when we use mass in this equation, we need it in grams. Now I know we've been using kilograms in all the physics chapters. This is the one exception out of all the equations where we will not have kilograms for mass. We need it in grams, so be aware of that. It's different than it has been for the last couple chapters. C is the value called specific heat. Now, we said that heat, the Q value, is dependent upon the mass, the temperature change, and then the material that the object is made out of. So what specific heat is, that C value, that's representing the material. So you're going to get that C value from a table of specific heats, and it's going to vary depending upon what substance we are looking at. For example, aluminum has a different specific heat than wood. Water has a different specific heat than ethanol or alcohol. So this would be a value you would get from the table based off of what substance the question is asking about. And we'll look at that table here in a moment. And last but not least, but we have this delta T. So we looked at that triangle, that delta sign before in the last chapter, and what that delta sign meant was change in. And whenever we have the change in anything, it's always going to be the final minus the initial. So you're going to take the final temperature and subtract the initial temperature to figure out the value of that delta T. When we're using this equation, we're going to have it in degrees Celsius. So this is where our conversion factors are going to become useful. If we are given the temperature in Fahrenheit or in Kelvin, we can always convert it to degrees Celsius if necessary. So here's that table of specific heats I was alluding to in the previous slide. So when I say specific heats, I'm talking about that C in the equation that I have highlighted in yellow here. So different substances have different abilities or capacities to absorb a given amount of heat. So looking at this table, for instance, think of stepping outside on a hot day. Would you rather step outside onto a metal deck or onto a wood deck? Okay, I would prefer to step out on wood because it's going to not feel as hot as a metal deck would feel. Well, why is that? It's actually due to the specific heat. So let's look at some examples. So let's say the deck was made of aluminum. Looking at the specific heat of aluminum, it's 0.215. Okay, so that is the amount of heat energy that it takes to raise aluminum 1 degree Celsius. Okay, well, let's look at wood. Its specific heat is 0.40. That means it has a higher specific heat. If it has a higher specific heat, it's going to take more heat energy to heat the wood up by 1 degree. So if it takes more heat to make it feel warmer, it's not going to get as hot as an aluminum deck would with a lower specific heat. So let's look at the units on specific heat, because this could help us remember equations and remember what units we need all of the variables in the heat equation in. So specific heat, the units are calories per gram times degrees Celsius. So if you ever forget what units are needed when you're solving for heat, just looking at this table of specific heats can help you remember. So we have calories. Well, calories, that's what our Q is going to be measured in, our heat. The G, that's grams. So that's our mass. Our mass needs to be measured in grams, not kilograms. And lastly, degrees Celsius, that's because of the temperature factor. We need our temperature in degrees Celsius. Before moving on to the next slide, I do want to point out that on this table, and this is just a very small table of specific heats because there's so many other substances we could look at, but out of the ones on this table, the substances on this table, notice that water has the highest specific heat. What that means is it takes a lot of heat energy to raise water by 1 degree. So that's a unique property of water. Water has the ability to soak up heat energy. It's higher than any other common liquid. 1 calorie per gram degrees Celsius. It's often the reason why it can be used in cooling car radiators. So if you've ever had a car that overheats and you don't have radiator fluid or some sort of cooling agent that's specifically formulated to cool your radiator, if you have water, that can work in a pinch. Because of water's ability, its high specific heat, its ability to soak up heat energy without raising the temperature of the car itself. So it can absorb the energy from your overheated car and still not heat up too much itself. Another unique property of water is that it solidifies and becomes less dense than the objects around it. What I mean by that is you make an ice cube, put it in the freezer, right? Well, when the ice is frozen and you put it in a water glass with some liquid water, what happens? The ice floats. That's a very unique property because the fact that the ice is floating means that the ice is less dense than liquid water. And most liquids when they solidify, are actually more dense than their counterparts and will sink to the bottom. So now we're going to talk about the conservation of heat energy. And we talked about the conservation of energy in the last chapter, and all that was that energy cannot be created or destroyed. It just is transformed from one form to another. So since heat is an energy, the conservation of energy also applies. So this conservation of heat energy states that when you have two materials of different temperatures, the heat transferred from the colder to the hotter will be the same. What that means is the heat energy lost is going to equal the heat energy gained. Okay, so if I lose 12 calories of heat from the hot object, the cold object is gaining 12 calories of heat. Much like with kinetic energy and potential energy. We have the acorn falling from the tree. If it had 12 joules of energy, potential energy before it fell, those 12 joules would have been converted completely into kinetic moving energy. So very similar theory, just applying it to a different form of energy. So in short, we have negative Q hot is equal to positive Q cold. So the reason for this is the reason why we have a negative sign in front of the hot is because the hot is losing the energy. So it's going to have a negative value, right? If you lose something, you're in the negative. You're in the red, right? If you gain something, on the other hand, like the cold is, you'll be positive. So the hot has a negative because it's losing heat. The cold has a positive because it's gaining heat. This is going to help us when we do lab 13, which shows the conservation of energy in that lab. All right, so let's look at this a little closer. And since I talked a moment ago about lab 13, this is kind of an example of what's going to be shown for lab 13 when you need to work on that. And what we're going to be doing is we're going to be taking some hot water and some cold water. We're going to take the temperatures of both the hot and the cold, and then we're going to mix those waters together. Okay, we're going to mix them and then we're going to stir it, because what we're trying to do is, since we have a hot object, hot water in this case, and a cold object, there can be heat transfer, right? The heat's going to transfer from the hot water to the cold water. So we're trying to measure this heat transfer with the thermometer. So in order to do that, since we know that the hot is going to lose and have a negative sign, it's going to lose heat, and the cold is going to gain and have a positive sign, we can take the equation for Q, mc delta T, mass times specific heat, times the change in temperature, and plug it in on both sides of the equation. In doing so, we can actually figure out what the final temperature of both of those mixed should be. And I'll show this calculation in a video with the other temperature conversion calculations as well. So here is a shortened version, just trying to figure out the delta T's. Remember, delta T is change in. Whenever we have change in, it's final minus initial. So if our final temperature of both mixed together is 37, to figure out the hot, we would take that number 37, the final temperature of both together, and subtract it from the initial temperature of the hot, which, as you can see below, is 50 degrees Celsius. Notice we have a negative change in temperature because the hot object loses heat. For the cold, we have the same final temperature because we mix the two hot and cold together to get the same final. They are now 1. We are subtracting 20 from it because that was the initial temperature of the cold water. And notice we have a positive change in temperature because the cold is actually gaining heat energy. So for a particular system, the heat content of the hot is always going to be less than 0 because it's losing heat energy, and the Q of the cold is going to be greater than 0 because it's gaining energy. They are equal to each other, but they're opposite. One's losing, one's gaining. So if you actually add the two together, they should equal 0 because the heat lost should equal to the heat cold. They're equal but opposite signs, so added together they should equal 0. And this equation below is just showing how they are equal to each other. So over on the left side of the equation we have m sub h, c sub h, and then delta T sub h. So those h's just represent mass of hot, specific heat of the hot, temperature change of the hot, so on and so forth. And that's why this one has the negative sign, because the hot is losing that energy. Then on the cold side we have similar, except for sub c's since it's the cold side. So here are a few equations that we're going to go through, heat example calculations using the equations that I have shown. So look for the video, perhaps watch the video after you look at this PowerPoint to see how to work through those. So let's talk now about heat, energy, and phase change. So when we looked at the original heat equation, it had mass in it, it had specific heat, which is dependent upon the type of material that we are talking about in the equations, and then it also had a temperature change. Well, those are 3 of the 4 things that heat depends upon. The 4th thing that heat depends upon is phase, and that's the one thing that's not present in the equation. So let's look at how phase change and heat relate to each other. So energy is required to melt a solid, more specifically heat energy. Because when you look at a solid, as you can see in the diagram below, the solid has little cohesive bonds, these little zigzag lines that you're seeing. And these cohesive bonds are holding the molecules together so that it stays a solid, so that it's not flowing, so that the molecules don't move. So in order to change this solid into a liquid, energy is needed to break those cohesive bonds. So all the energy that's going into this system is being used to break these bonds, setting the molecules free, turning it into a liquid. So energy is needed to go from solid to liquid. Same thing applies if you go in the reverse direction. So if I'm trying to go from a liquid, so these freely flowing molecules here, into a solid, in other words, freeze those molecules, there's actually going to be a release of energy. So we talked about heat and phase change. We just said that heat was needed to go from a solid to a liquid, as well as to a liquid to a gas, because energy needs to be input to break those cohesive bonds. Well, let's look at temperature and phase change, because temperature and heat are very closely related, temperature being a measurement of the heat content going into the system. Now, the thing about phase change, though, is that temperature does not change, rise or fall, during phase change. So looking at this table over here, the phase change from solid to liquid is happening right here in red. And notice, this table is talking about water, so at 0 degrees Celsius, that's the temperature at which water freezes. It's also the temperature at which water or ice melts. So when we get to this stage, right at 0 degrees, all the heat that's going into the system, it's going toward breaking those cohesive bonds. It's going towards making that phase change, making that solid go into a liquid. So all that energy going into the system is just breaking those cohesive bonds. And it's not allowing a temperature change because that energy is going towards breaking the bonds rather than in changing the temperature. Once the phase change is complete, so once all of that ice is melted, then you'll notice the liquid will start heating again. And it can therefore heat until it gets to 100 degrees Celsius, because that temperature is the temperature at which water boils. And when water boils, that's another phase change, because at boiling point, you're turning the liquid now into a gas. So liquid to a gas is a phase change, so when we get to that point, all the energy going into the system, all that heat energy, is going towards making that conversion, that phase change, making it from a liquid to a gas. So we don't see a temperature change because there isn't enough energy to do both. Once all the water boils, however, it can start heating up once again. This heat energy that is required during a phase change, this energy that is required to turn a solid into a liquid or a liquid into a vapor, is called latent heat. So the reason it's called latent heat is because what latent means is hidden. So you'll notice I said that phase change wasn't included in that equation that we looked at for heat. The equation was Q is equal to mc delta T. So we had mass, we had specific heat, which was dependent upon the type of material, and we also had a temperature change. Well, we just said that during phase changes, there are no temperature changes. So this is not a measurable amount of heat. It's called hidden heat because it's not something that can be measured through temperature. So latent heat, by definition, is the heat required to turn a solid into a liquid or a liquid into a vapor, and it occurs only during phase changes. So from solid to liquid or liquid to gas. That's heat going into the system that's going in towards breaking those cohesive bonds, that's going in towards making the phase change happen. So it's the energy that's entering or leaving the system without actually changing the temperature. And this amount of energy it takes is going to depend upon the strength of the molecular forces of that system. So looking a little closer at latent heat, I want to apply it to some examples. Ice melting. So I have that in the first picture here. So ice melts at 32 degrees Fahrenheit or 0 degrees Celsius. So if you have a glass of ice water sitting on the table and you had a thermometer in it, it would read 32 degrees Fahrenheit. Now your ice would be actively melting because you'll notice less ice as time went on. You'd actually get to a point where all of the ice has melted. But if there's any ice in that glass, your thermometer will read 32 degrees Fahrenheit. However, you know that heat's going into the system because otherwise your ice wouldn't be melting. So that heat that's going into the system that's melting your ice, that's latent heat. The temperature isn't changing at all, but heat's going to the system because your solid ice cubes are going into a liquid form. So they are having a phase change. Once all the ice melts, you'll notice the temperature will now rise from that 32 degrees Fahrenheit on up. Boiling water, similar example. Phase change, we're going from a liquid to a gas in this case. You can have a pot of water on the stove. Heat it up, it can be actively boiling. And if you have a thermometer in there, it's going to say 100 degrees Celsius or 212 degrees Fahrenheit. Now that temperature is going to remain the same, but you know heat's going into the system not only because your stove is on and you can see the flame below it, but also your water level's going down. So you know you're losing water molecules because they're going into a gaseous form. However, you're not seeing a temperature change because all of the heat going into it, all that latent hidden heat, is going towards that phase change. The last part of the chapter, we're going to look at some methods of heat transfer. And what we have are conduction, convection, and radiation. With conduction, this occurs through direct contact. So an example in this diagram here would be this person holding the handle of the pot. So they are in direct contact with that handle. They can feel heat transfer through that direct contact. Convection. This involves fluids. It can also involve gases as well, but the example in this diagram is the water because it's a liquid. What we have are the liquid molecules at the bottom of the pan are heating up faster than the molecules at the top. So this water at the bottom is actually warmer initially. How does it make the rest of the water warm as well? Well, since these molecules are in contact with each other, they are transferring their heat from molecule to molecule, heating up the top water as well. The last example, radiation, this is through indirect contact. So that would be the fire heating the pot. Like, you don't actually have to put the pot in the fire to get the pot warm. It can actually heat up through indirect contact, through feeling that heat transfer without touching. So looking at these a little bit closer, conduction we said was heat transferred when two substances are in contact and are not moving. So this example here has a person holding a needle in a candle. Well, what happens if you hold something metal in anything that's hot? Well, that metal is going to heat up as well. It has a low specific heat, as we saw in that specific heat table. So the temperature of that needle is going to be raised very quickly. With your hand in contact with that needle, you're going to feel that heat transfer through that direct contact. Another example is warm feet on a cold floor. If you get up in the mornings and it's a little bit of a chilly day, you can feel the cold floor beneath your feet, and your feet are actually transferring heat from your feet to the floor. That's why your feet get colder and the floor gets warmer. Insulation can also slow the transfer of that heat conduction. It's often the reason why socks or slippers help on a chilly morning, because by having that insulation, that heat transfer doesn't happen as quickly. In lab, for lab 13, when we are doing the experiment with the conservation of heat energy, you'll notice that we are using styrofoam cups. Fancy word for that is a calorimeter. And what that styrofoam cup acts as is insulation, so that we're not losing any heat, or at least losing less heat than we would if it was a paper cup or some other apparatus that didn't have an insulation barrier. With convection, it's the mixing of hot and cold components or fluids. So the higher temperature molecules are transferring heat to the lower temperature molecules. Now this happens most often with liquids, but it can also be gases, anything that flows. So the key here is that they're moving while they touch. So with conduction, we had two objects touching, transferring heat, but not moving. With convection, we have two objects that are moving and touching and transferring heat. And it applies to liquids and gases because both liquids and gases flow. Convection stops when the temperature evens out. So the pot of water we saw in the original example, another example of this would be air conditioners or even just heat in your house. So you have hot air being pumped into your house. That hot air is mixing with the cold air, transferring that heat through those two gases touching each other but moving, evening the temperature out in your house. Radiation is the last form, and this is two substances in which neither touch or move for heat transfer to occur. So I used a fire in the original example. The example here would be the sun warming the earth. The sun is not touching the earth, yet we can feel its warmth. If the sun rays were touching the earth, we'd all be done for. So this is a form of radiation. We can feel the warmth, the heat transfer, without any actual contact. Other forms are microwaves. Microwave can heat up your food without direct contact. Magnets, X-rays, a fire is even another example. You can put your hands near a fire and feel its warmth, feel that heat without actually touching the fire. This last slide is just bringing together those three methods of heat transfer we talked about and just showing how they are all around us. So we have convection around the windows because we have cold air and hot air mixing together. Radiation from the fire, so no touching there, right? You can feel the fire's warmth without coming in direct contact with it. We also have conduction, so the example here being those hot logs on the floor, direct contact, both objects not moving and heat transfer occurring. And then we also have another example of convection with the hot air from the fire mixing with the cold air in the chimney.